Good day, guys. We are in the process of looking into what are the different protocols that has been used by the QKD quantum key distribution. So the first classical protocol is the BB84, which I have seen that two different bases are used during the photon creation, and that will be adhered towards that. Now we'll be looking into another popular protocol that is called E91. So it has been named after the inventor, uh, right? And Anku Aircut. I hope so, right? I may be misspelling it, right? Missounding it. But the protocol is E91. So we do have one more protocol, right? That is called BBM92. So we'll be seeing in detail about this BB92 later, but you just be aware we are having one more protocol that is called BBM92, and this is actually the, we can say, extended version of BB84, right? But and here we have seen that Bennett and Brassett, right? But here we have one more inventor called Mermin. This guy was doing the extension work of this BB84, and it was labeled as a BBM92, and this 92 is the year, and here also 91 is the year of the invention. And all these protocols are meant for QKD, quantum key distribution, in the quantum computation, especially in the quantum cryptography, to make the secure transaction between the sender and receiver. So the key difference between this E91 and BBM92 is actually, right, this E91 was using the Bell inequality, whereas this BBM92 is using quantum bit error rate, QBER. So this is the key difference, but we have one common, right, strategy or technique that is used by E91 and BBM92. That is, both use the entangle photon in their protocol. So this is a common technique used by both E91 and BBM92, but both use a different strategy to make this entangled photon to be exploited between the Alice and Bob, that is sender and receiver, and to ensure how the secure quantum channel is used to share the information, so that the intruder or stranger cannot eavesdrop it. Alright, now we just go with this E91, which is using the Bell inequality, right? And this Bell equality is purely a mathematical computation, right? It's further, used by CHSH. We no need for the inventor name, all those are inventors, right? CHSH, who actually uses the notation S, and this Bell, right, inequality will be always checking for this S. If it is less than or equal to 2, then that is the Bell inequality, right? It's a Bell inequality. If S greater than 2, that is violating Bell inequality. So just remember this, it's a pure mathematical background, right? So just remember that. So now if we are saying the Bell inequality is satisfying, that is greater than, sorry, less than or equal to 2, then we can say it's the classical world, right? The communication between the Alice and Bob resides in classical world. But if s greater than 2, then the Alice and Bob have the communication in the quantum world. And this in fact used by the Bell inequality over in the E91 protocol to ensure the transaction between the Alice and Bob, that is sender and receiver, is secure and was not eavesdropped by the Eve. So to start with, we first understand this Bell inequality. We already told some notation is, and this is actually formulated by AB plus AB plus AB minus AB. Just have this, right? Like the formula what we used to learn, right? A plus B whole squared. Similarly, we have the mathematical notation over here. And for understanding, we can say this A and B, it's an Ali's measurement and it's a Bob measurement, right? And now, coming back to the core idea behind this, just for instance, right, if we are saying, right, an entangled photon is created, what in fact it means, we already know what is entanglement. So entanglement is something, right, an intangible connection, right? So that if we measure at one end, then we no need to measure at the other end. We can deliberately say what will be the outcome of the other one. That we often used to say, the classical good example is when we are having two box of ball. One box is a red color ball and another box with a blue color ball, and one box we are opening, that is we are measuring, and another box it was kept far away. We doesn't even know that what color of ball it was there earlier, right? Now we are opening at one end, and if we are seeing a blue color ball, then without opening an other end box which is very far away, we can say it would be the red color. Why? Because we do know the only the two outcome is possible, that is a red ball or a blue ball. So if we are coming with a one measurement, if it is a red ball, then the other would be certainly it's a blue ball. The other way around is also possible. So this what actually the entanglement means, and the entanglement photon is used in quantum cryptography to make the quantum channel more secure. So an entangled photon could be created by the external source, or it can be created by the allies too, right? Or the sender, you can say like that, right? Or a sender. So the sender or external source will be creating an entangled photon, and that will be shared to an uh, Bob. If it is an external source who is creating the entangled, say for instance, right, we are having the source, right? This source is an entangled photon. Then he will be sending to Alice and Bob, right? Or sometimes this Alice, right, external, right, we can say that is the entangled photon, that the source is with the allies, then he himself creating an entangled photon, and he is sending to the Bob. Anything, both are fine only, right? So now the concept behind it. So the entangled photon is shared to the receiver. Now what are the random measurement we do have? So and we are in the quantum world, so the allies is also in a superposition. Bob is also in the superposition, until both are doing a measurement in their own photon, right? Now allies can have either A or A dash, right? That is, it could be a 0 or 1. That's correct. Now we know the classical bit 0 or 1, but until the superposition, superposition is not measured, so we'll be having a probability of zeros and ones, right? That is the concept behind the quantum probability of zeros and ones. So allies would have the random 0 or 1. Similarly, Bob would have the random B or B dash, that is zeros or 1. So now the possible right would be A dash, B dash. So it could be a 0, it could be a 1, it could be a 0, it could be a 1, right? So again, based upon the polarization, A could be a 1, A dash could be a 0. It depends, right? But conventional understanding is this the way, right? Now we know, right? This Bell inequality always resides like plus 1 minus 1. So this can be said as a 0, this could be said as a 1, right, for an understanding, because 0 and 1 cannot create a correlation, right, while computing mathematically. This is very important. While mathematically, right, computing, this correlation will be a bit fuzzy, so we are going for plus 1 minus 1 representation. So for instance, right, for instance, we can call the two students to imagine any value for A dash, B dash, right? This is Alice, this is Bob's, and the given value is plus 1 minus 1. So we have called two students, we are making them to assign plus 1 minus 1 for this A dash and B dash. They can have all plus 1, they can have all minus 1, they can have plus 1 for A, minus 1 for A dash. It depends, right? So it can be of anything. Now we are just computing. Just imagine we have A is plus 1, A dash is minus 1, B is plus 1, B dash is minus 1. Now this Bell inequality, we do have S is equal to AB plus AB plus AB minus AB, which in fact means this is one correlation, this is one correlation, this is one correlation, this is one correlation. So this AB, Alice and Bob can have a same value. This is one possibility, correct? So that is Alice would also have a plus 1, Bob would also have a plus 1. We are just checking for the correlation probability. Now in other hand, Alice would have a plus 1, right? Bob would have a minus 1. Now the third term, Alice would have a minus 1, Bob would have a plus 1, and finally Alice would have minus 1, Bob would also have a minus 1. So all the different combination we are trying to correlate, right, and find out whether S is less than or equal to 2. In that case, Bell inequality appears. Means we are in the classical world. But if in case S is greater than 2, not equal to, is S greater than 2, then we are in quantum world. So usually it measures with 2 point, right, 2.8, or right, proven one as a 2.7, right, 2.7. So which itself says it's a quantum world. So this is what we are trying to prove in the Bell inequality while we use for the E91 protocol. So even that example, right, this particular example. So what happened? Plus 1, plus 1, plus 1 into plus 1, of course plus 1. Then plus 1 into minus 1, plus 1 into minus 1, it became a minus 1, became a minus 1, plus minus 1 into plus 1, again it became a minus 1. Then again minus 1 into minus 1, it became a plus 1. So now just do it, right? Plus 1 plus minus 1. So plus 1 plus, here we can say, right, sorry, so 1 plus into minus, minus 1 minus 1, and again minus into plus, minus 1, right? So correct now. So 1 plus into minus, minus, so minus 1, and plus into minus, again minus 1, and finally minus into plus, minus 1. So we do have 1, minus 1, minus 1, minus 1, minus 1, and minus 1. So minus 3. So 1 minus 3, it would be a minus 2. So just ignore minus, right? It's an absolute value. So it comes with a classical world. So this how Alice and Bob will try to find whether the Bell inequality is getting failed. So if it failed, then they assure, okay, then the entanglement is secure, and so the key is secure or not intrude by the stranger, or at times we call as a EU. So it's easy to understand.